You know that feeling. Driving a really high-performance car, you shift gears, and it's just click. Perfectly smooth, instant power.
Oh, yeah. Seamless. Like it read your mind.
Exactly. And then think about the opposite. That clunky shift, maybe it hesitates, or worst case, it gets stuck.
Ugh, yeah. Completely throws you off, kills the whole experience, and maybe even control.
It's such a massive difference, isn't it? And the thing is, we often think it's just about the engine, the raw power.
Right. Horsepower gets the headlines.
But it's really about the precision of the whole system, everything working together perfectly. And today, that's what we're diving into. The super intricate world of tolerance interval analysis, specifically in these high-performance sports cars. We're focusing right in on those gear-shifting mechanisms.
And that's our mission today, really, to unpack how that level of engineering precision, we're talking tiny variations in parts, how that affects, well, pretty much everything.
Speed, acceleration,
Fuel efficiency, and, maybe surprisingly, even the final production cost of the car. It's a fascinating link.
from the design on paper to how it actually feels on the road.
Exactly. And we'll explore how these advanced analytical strategies are, frankly, revolutionizing things, moving us way beyond just trial and error.
So our guide for this is some really interesting research. It's called Analisi degli intervalli di tolleranza a prova di cambio.
Right.
Which, roughly translated for us, is something like analysis of tolerance intervals for a foolproof gear shift.
Foolproof. That's the goal.
Yeah, written by Ortis and Juan Lopezdealda, just published June 25th, 2025. And it really digs into this question. How can these tiny engineering tweaks, these adjustments in tolerance, lead to such huge improvement?
Performance and cost. It's intriguing.
Okay, let's get into it. How do these tiny details make such a difference? So maybe we should start right at the heart of it. The gear shifting mechanisms themselves, they're absolutely critical.
Well, fundamentally, you think sports car, you think engine, maybe aero.
Right, the flashy stuff.
But the shifter.
Yeah.
That's how you actually use the power. It's not just a lever.
No, the source makes that really clear. It determines the quality, the effectiveness of the shift.
Yeah.
Speed, acceleration, even fuel use. It all comes back to how well that shift happens.
Every millisecond counts in performance driving. Yeah. Any loss of power, any hesitation.
It matters. You want that connection, right? Like the car is just an extension of what you want to do. Seamless, powerful.
That seamless experience. And that's where the engineering challenge really comes in.
Okay.
So individual parts, a gear, a shaft, whatever, they have specific load tolerances.
Okay.
Basically, how much variation is allowed by the design so they don't break.
Standard engineering stuff.
Right.
Yeah.
But the real complexity, the real headaches, start when you assemble them.
When they all have to work together.
Precisely. The crucial thing becomes accuracy in how they interact. You've got this kinematic chain, a series of connected parts moving together.
Like links in a chain, transferring the motion.
Exactly. And even with super precise manufacturing, parts can have these tiny, unexpected, relative movements within that chain.
Not flaws necessarily, just reality.
Just the nature of manufacturing variability, however small. But these tiny shifts, maybe a bit more movement than planned, maybe a bit less, they can stack up.
And cause problems down the line.
Big problems. Performance issues, disrupting that seamless feel you were talking about.
Yeah, and this is where the source material gets really interesting for me. The design team they studied, they weren't just trying to fix problems.
No, they were optimizing.
Right, and they found something counterintuitive. We usually think better performance means higher cost, tighter tolerances, more expensive manufacturing.
The usual trade-off.
But listen to this quote from the team. Thanks to this analytical strategy, it was possible to quickly identify potential failures and modify the tolerance intervals. This optimized the mechanism's responsiveness, allowing changes to reduce overall production costs.
That's the key part. Optimize responsiveness and reduce costs.
Blows my mind a little. Better performance, lower cost.
It's about being smart with precision. Using these specialized tools to test different tolerance levels. Figure out where you really need that extreme precision and where maybe you don't.
So tightening some tolerances, but maybe loosening others.
Exactly. Improving responsiveness and cutting costs by not over-engineering where it doesn't matter. That idea of smart precision, that's the breakthrough.
Okay, so let's dive into that smart precision idea. It hinges on understanding manufacturing variability, right?
Absolutely. No matter how carefully you make a part, there will always be tiny deviations from the perfect nominal dimension. A few micrometers here or there.
Invisible to the eye, basically.
Pretty much.
Yeah.
But when you assemble dozens of parts, these tiny variations add up. It's called tolerance stack up.
Okay.
And the precision of the whole mechanism, like our gear shift, depends not just on how accurately each part is made, but how these tiny variations interact across the entire assembly.
And every single assembly might be slightly different.
Potentially, yes, because the combination of variations will be unique. So understanding how each design variable, each tolerance influences the final function is critical. You need to know which variations matter most.
So how on earth do engineers manage that? All these tiny interacting variables, it sounds incredibly complex.
It is, and that's why they rely on things like virtual prototypes, which the source mentions.
Digital simulation.
Exactly. They build a detailed computer model of the gear control system, focusing on this specific kinematic chain, the series of parts involved in the shift.
A digital twin.
A very precise one. It lets them simulate everything without building endless physical prototypes, which is slow and expensive.
And the goal for this specific mechanism?
Fluid, precise movement, obviously, but also rapid gear changes. Crucial for performance cars. Milliseconds matter.
Any hesitation is bad.
Very bad. Whether you're on a track or just merging into traffic, this virtual environment lets them test scenarios, push limits, see what breaks, all digitally.
And that virtual testing helped them understand real-world problems like partial lock and total lock.
Precisely. Figure 1 in the source shows it well. Imagine a yellow part guiding a blue part to select the gear. Simple sounding, but it's the result of a 9-part kinematic chain working together.
9 parts interacting just for that one movement.
Right. Ideally, shifting, say, 7th to 6th, the blue part follows a nice, clean path. But what if those tiny tolerances stack up the wrong way? In a partial lock, maybe the blue part nudges past where it should on the yellow guide.
So it gets slightly stuck?
Kind of. The driver can often force it, push through, but it feels wrong. It's resistant, clunky, maybe a crunch.
Not the smooth shift you expect in a performance car. It feels broken.
Exactly. It shakes your confidence, impacts performance. It's jarring. Then you have total lock. That's the worst case.
Complete jam.
Yep. The stack tolerances are so off that the blue part gets completely blocked by the yellow guide. The driver physically cannot move the lever into that gear. 7th to 6th? No. Stuck.
Wow. Imagine that happening on a racetrack, heading into a corner, needing that downshift.
Or even just in traffic. It's not just inconvenient. It can be dangerous. You lose control, predictability.
And the simulation showed why it happens.
Yes. It showed that sometimes a tiny backward movement is needed first to clear the interference. It highlights just how precise these interactions need to be. Microscopic misalignments can cause total failure.
It really brings it home, doesn't it? Thinking about being in a race or just needing to react quickly and the gear shifter just locks. Suddenly these tiny tolerances feel very real, very tangible.
Absolutely. It's not abstract anymore. It's about safety, performance, and just the basic function of the car working as intended. The stakes are incredibly high.
Okay, so we have these potentially catastrophic problems, partial lock, total lock, caused by tiny variations. How do engineers actually fix this? How do they perfect the design?
Well, they need a systematic way to define the right tolerance intervals for all those parts in the kinematic chain. It can't be guesswork.
Right, too expensive, too slow.
Exactly. The source mentions a general analytical procedure, shown in their figure 2. It's about using the right tools in a structured way.
And the tools they used were key here.
Absolutely. 2 main software tools from Hexagon. First is Atoms.
Okay, what does Atoms do?
Atoms is what's called a multi-body dynamics simulation software. Basically, you build a virtual model of your mechanism, the gear shifter assembly, in this case.
The digital twin again?
A very dynamic one. You can simulate how it moves, the forces involved, how it behaves under real conditions. You can define your design goals within Atoms.
Like achieve shift in X milliseconds.
Exactly. And crucially, it has a module called Atoms Insight that lets you run preliminary design of experiments, or DOE.
DOE, design of experiments. What's that involve?
It's a smart statistical way to test how different input variables like the tolerances on each of the 9 parts affect the outcome, like shift smoothness or locking. Instead of testing random combinations, it systematically explores the possibilities.
Efficient exploration.
Very. Atoms Insight generates this big matrix of data showing how the mechanism performs across a whole range of tolerance combinations. It maps the behavior. Okay, so Atoms builds the virtual world and runs the initial experiments, generating lots of data. What's next?
That data matrix becomes the input for the second tool, Odyssey C Lunar, also from Hexagon.
Odyssey.
Think of Odyssey C Lunar as the intelligence that learns from the Atoms data. This is where the speed comes from.
How does it learn?
It uses that huge data set from Atoms to build what's called a surrogate model using machine learning. It's essentially a super fast mathematical representation of the complex atom simulation, so it learns the relationship between tolerances and performance.
Exactly. It understands how changing tolerance A affects outcome B and how it interacts with tolerance C based on all the data atoms provided.
Okay, I think I follow.
Once it has learned this, Odyssey doesn't need to run slow, complex simulations for every new idea. It can predict the results for new tolerance combinations almost instantly by querying its learned model.
Ah, so it's predicting based on what it learned, not resimulating everything.
Precisely. That's why you can analyze new scenarios in minutes instead of the hours atoms might take for a full simulation run, and can assign new tolerance intervals within the learned ranges to see the predicted effect.
So it's an iterative loop. Adams does the heavy lifting first, Odyssey learns and predicts quickly, feeding back insights.
Exactly. Odyssey provides sensitivity results showing which tolerances matter most.
Uh-huh. The smart precision part.
Yes. Based on that sensitivity, engineers create a new, refined DOE, maybe back in Adams or directly in Odyssey, with updated tolerance intervals tighter where needed, looser where possible.
And the goal.
Optimize function at lower cost. You repeat the cycle, refining further each time, covering more possibilities, zeroing in on the best, most cost-effective design. It's learning-driven optimization. And this process really highlights something fundamental, doesn't it?
Yeah.
That even if two parts seem fine on their own,
Put them together in a chain.
with multiple other interacting parts, the tiny individual variations can accumulate. They stack up.
Sometimes in unexpected ways.
Absolutely. It might not be a simple addition. You can get these emergent effects, leading to bigger or smaller movements than you'd predict just looking at two parts. Linear or angular displacements get thrown off.
And it's that accumulation, that cascading effect, that these tools help unravel.
Precisely. Managing that complexity is what Adams and Odyssey are designed for.
Okay, theory and tools make sense. Let's get concrete. The case study in the source. How did this actually play out on a real mechanism?
Right. They applied this exact process to analyze a gearshift mechanism specifically to see how these tolerance intervals accumulated along the kinematic chain.
Putting the theory to the test.
Exactly. First, they ran a simulation in Adams' view with all components at their nominal dimensions.
The perfect world scenario. Ideal parts.
Yes, the baseline. How it should work in theory. This confirmed the basic design concept worked under ideal conditions. Then came the second simulation, using Adams' insight and that design of experiments, DOE approach.
Okay, introducing the real-world tolerances.
Exactly. They plugged in the actual manufacturing tolerance ranges for each part. Now, instead of one ideal outcome, the DOE mapped the behavior across the whole spectrum of possible tolerance combinations.
And this is where problems would show up.
Yes. This simulation identified the range of responses, and crucially, it pinpointed specific combinations of tolerances that resulted in malfunction.
The partial and total locks.
Precisely. It gave them the data showing when and why the mechanism failed, linking it back to specific tolerance interactions.
Okay, so Adams' insight identifies the problems and the conditions under which they occur. Then Odyssey steps in.
That's right. All those results, the good and the bad, the whole map of behavior from Adams' insight, that becomes the input data for Odyssey Lunar.
Feeding the learning machine.
You got it. Odyssey processes that data, builds its surrogate model, and then can rapidly show the predicted response for countless combinations of tolerances.
Faster than rerunning Adams' simulations.
Much faster. But critically, it also provided the sensitivity results for each tolerance.
Showing which tolerances were the big players, the ones really driving the problems or ensuring success.
Exactly. Which ones had the most leverage on the system's behavior.
And with that sensitivity knowledge,
they could create a new, optimized DOE right there within Odyssey. This is where the targeted changes happen.
Okay, what did they change specifically?
Based on what Odyssey's sensitivity analysis revealed, 3 tolerance intervals were reduced by 40%.
Tightened up significantly. Must have been critical ones.
Presumably the ones Odyssey flagged as having a high impact on function, worth the extra manufacturing cost.
Okay. What else?
5 intervals were increased by 33%.
Loosened. Made less precise.
Correct. These must have been areas Odyssey showed had little impact on the key performance metrics. So, save money here.
Makes sense. Any others?
And 4 tolerances were actually doubled, increased by 100%.
Wow, doubled. That really suggests they were massively overspecified before.
It seems so. Areas where extreme precision just wasn't necessary for this specific mechanism's function, according to the analysis.
So targeted tightening, significant loosening elsewhere. What was the result of all these changes?
The outcome was impressive. These modifications led to an 8% reduction in partial lock occurrences compared to the original design.
8% fewer clunky, jarring shifts. That's a noticeable improvement in feel and reliability.
Definitely, especially in a high-performance context. It's about consistency and driver confidence. And it came not from making everything tighter, but from making precision smarter.
That's the performance side. What about the efficiency side, the speed of this process?
This is where it gets really remarkable. The source states that these tolerance modifications also led to significant production cost savings, which we expected from loosening some tolerances.
Right.
But the time it took to run this new optimization loop within Odyssey Pay,
How long?
less than 2 minutes.
2 minutes to analyze all those changes and predict the outcome.
Yep. Compare that to the original Adams Insight analysis, which they said took about 10 hours of resolution for one comprehensive DOE run.
10 hours versus 2 minutes. That's not just faster, that's a different dimension of speed. A total game changer for the design process.
Absolutely. It means engineers can iterate incredibly quickly, test more ideas, explore trade-offs, and find optimal solutions in a fraction of the time. It accelerates development massively.
So the speed comes from Odyssey having learned the system's behavior from that first big Adams run.
Exactly. Adams provides the detailed physics-based foundation. Odyssey builds its fast, predictive surrogate model from that foundation.
Like learning the rules of the game from watching many matches.
A good analogy. Once it knows the rules, the relationship between tolerances and outcomes, based on the sensitivity analysis, it can predict the result of new plays or new tolerance combinations almost instantly using its internal model.
No need to resimulate the whole game from scratch each time.
Precisely. It's applying learned intelligence. And that process revealed something really key, didn't it? About which tolerances could be changed.
Yeah, the fact that some could be increased so much doubled, even.
Right. It showed they had very little influence on the critical responses. You could make those parts cheaper to manufacture without hurting performance. That's a huge insight for cost reduction.
While others clearly needed tightening, showing where the precision investment really paid off.
Exactly. It challenges that old idea that more precision is always better.
It's not just more, it's smarter precision, knowing where to apply it.
That's the core takeaway. Focusing resources manufacturing effort cost only where it delivers real functional benefit, optimizing the use of precision.
So bringing it all together then, this analytical strategy wasn't just about fixing one problem.
No, the source emphasizes it gave the team a methodology, a way to efficiently iterate, explore different scenarios just by varying tolerances in the Odyssey model.
And the result wasn't just better performance, but
a significant reduction in production costs. That's the powerful combination. Better car, cheaper to build.
And that cost reduction came specifically from being selective.
Extremely selective. Tolerances were only expanded, made looser and cheaper, where the analysis proved their impact on function was negligible.
No negative side effects.
Right. And conversely, they only tightened tolerances, adding cost, where it directly influenced the critical aspects of the mechanism's performance.
Smart allocation of resources, precision where it counts, savings where it doesn't hurt.
Exactly. It's about designing for performance and manufacturability together, using data to guide those decisions, not treating them as separate problems.
It really is an elegant approach, designing this optimized system that delivers that high performance, that foolproof shift, but keeps costs contained. It kind of breaks that traditional assumption of performance always costing more.
It does. It shows what's possible when you leverage deep analysis and these advanced simulation and learning tools. You get superior products and more efficient manufacturing. It's a win for the company and a win for the driver.
Absolutely. And, this whole deep dive into gear shifts, it's more than just about sports cars.
You think so? Yeah, I mean, it's a fantastic example, right? How understanding variability, how parts interact down to the micron level, and using smart tools to manage it, how that unlocks huge improvements.
In performance, in cost, in reliability.
Right. It just reminds us that real innovation often happens in refining the details, finding those surprising efficiencies through intelligent analysis, not just grand sweeping changes. It's about mastering the complexity.
It really makes you think. So the next time you're driving and you feel that perfect, satisfying click of a gear change,
that seamless connection.
Maybe pause for a second and consider that invisible dance happening underneath. All those tolerances, perfectly balanced, optimized by software that learned how they all interact.
It's pretty amazing when you think about the engineering behind it.
It really is. And it leaves you wondering what other complex systems around us could benefit from this kind of depth dive. Your washing machine, the city's traffic light system, medical devices.
The possibilities seem endless, don't they? Anywhere there's complex interaction and variability.
Applying this kind of analysis, finding those hidden efficiencies, optimizing performance and cost. Imagine a world where everything just works perfectly.
That's the goal, isn't it?
Yeah.
Limitless potential, really.